Hello and welcome to the week 4 set of videos for csc314 assembly language. And I'm going to kick off as I'm starting to get people asking questions. So I'm going to kick off with a question that came into me from email. Hopefully the answer to this will be helpful to others out there. Perhaps some of you already understand what's going on here. But the question is, how would you count beyond 127 with signed binary integers? Now, I assume that this question is referencing these two charts and the discussion that went with these charts. Here I'm showing the 2's complement representation, but it's important to keep in mind that this is only applicable to 1-byte integers here. So let me highlight that. Or let me just put some additional text in here. This diagram applies to 1-byte or 8-bit integers, signed integers. If you had more bits, such as 16 or 32-bit integers, you would need a bigger circle. I think I said that, but it wasn't written, and it's something that easily could have slipped past your notice. Yeah, so if you think about the way negative numbers work in signed integers, then yeah, you're always limited, right, in what you can represent. Here you can only go with a 1-byte integer, i.e. a car in C programming. You can only get up to 127 as positive, then it rolls over to a negative 128 and rolls right around counting, well, it's still counting, it's counting up, but from negative 128 up to negative 1, and you get back around to 0 here at the top, right? So, so if you felt like, well, that's the only way you could represent the integers was this way, then you're stuck with this small range. But obviously, you know, in C programming and so forth, you have regular int, which are 32-bit that go up to about 4 billion, then you have long, which use 64 bits. So basically what we can say here is, for example, a 32-bit integer will go from 2 to the 31 minus 1. That's going to be the maximum positive number. So we go from 0 to 2 to the 32 minus 1. Let me put that in parentheses so it's clearly a number. Then we have negative 2 to the 32. Okay, actually I don't need the parentheses for that. That'll work. And then then to negative 1. All right. So hopefully that's clear how you can extend the idea of this circle for 32-bit numbers, or, you know, if it was 64 bits, 8-byte numbers, you would go 0. Actually, I can probably copy and paste faster. So here inside of 32, we have 64 and 64 like that, and so on. So this is for signed integers. And just for completeness, let's keep the 8-bit in there. So there we're going from 0 up to the 8th minus 1, and then negative 2, I'm sorry, not to the 8th, 2 to the 7th. I was forgetting to subtract 1 from the exponent here. Yeah, those other powers, those will come into play. I might as well, you know, make it applicable for this, show you the sign, unsigned as well here, which I'll do in a moment. So this is going to be 2 to the power of 7 and dot 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 and around to -1. So you can see how each of these, depending on the size, you have a different range of values, but they all do basically the same thing. And then for unsigned, you still have the same limitation. Like for unsigned integers, you go from 0 to 255. Okay, 255 equals 2 to the power of 8 minus 1. That's where that comes from. Maybe I should say it this way. I'll put the 2 to the power of 8 minus 1. So we're looking at the power the same way we are above. And then similar for the larger ones. So we can copy and paste and paste. So if you wanted to do 32-bit, I suppose I could put a line in here for 16-bit as well, but I think hopefully you get it. These are the most common ones to be used anyway. And whoops. Oh, I see what I did. There we go. Actually, I think that stuff in the parentheses makes it too busy. I think I'll just do it like that. All right, so what I would do is I would suggest Google and compare to min-max values for different integer types in C. So if you've done some C programming, which almost all of you have, probably all of you have, you're familiar with the different types. So look up the min-max value of different types in C. Car, int, long, and so forth. Keep in mind in C, a car is really just a 1-byte integer. So, and you have, and not just the different integer types, but the signed and unsigned versions. So I'll leave that as a little bit of an exercise for you to go out and Google that and then compare to my table of numbers here. So yeah, so keep in mind that this diagram applies only to 8-bit signed integers. And if you want larger, if you have more bits, then you just end up with a bigger circle. Likewise, this table is for 8-bit integers. So we're looking at signed and unsigned car from C programming. Okay, so just to make it as crystal clear as I can, what's going on. So this table only applies to 8-bit binary integers. We have the signed and unsigned values on either side here. And our number systems diagram, likewise, this is only going up to 8 bits, except for the last row, we jump to needing a 9th bit to get to 256. So the thing I want to come back to is, on the original question here, is how would you go beyond 127? Well, you don't if you only are using an 8-bit integer. So basically you don't count beyond 127 with signed 8-bit integers, i.e. car from C. However, what I will say is, if you do, you wrap around to the negatives. Let me just be specific. You wrap around to negative, let me just say minus 128. Okay, so, but the same problem exists for unsigned 1-byte integers. Okay. Why did it? There we go. If you count past 255, you wrap around back to 0. So, so just keep that in mind. It's really not signed and unsigned integers work entirely the same way. In fact, the same binary representations are going around the circle. So if we come back to the circle, we can put unsigned integers around here, and instead of wrapping around to 128, you'd go to positive 128, and you just keep counting up to 255. So you can go either, but you basically have the same binary representation on the circle, and once you get to the maximum binary value, all ones, then you roll over and wrap around to all zeros. So they both work the same way, and the convenient thing is the underlying method of doing arithmetic with signed and unsigned integers is entirely identical. You add and subtract them and everything exactly the same way. And so the CPU actually does not know and does not care if you give it a signed or unsigned integer. So I'm going to throw that into my little notes here. So, interesting fact, the CPU does not know or care if you are working with signed or unsigned integers. It is up to the software to know what it is doing. So if you add, say 77 plus 88, well, let's see, in binary that's going to go, let's say we're working with 1-byte ints. I'm just doing bytes because, for examples, they're small. So let's say we take 77 plus 88. All right. What is that in binary? Well, let's see. Binary 77, that's going to be 0010. Let's see. That's 77 minus 66. I have 11 left over, so I think I need 8011. Yeah. So that's that. Plus, now 88, that's going to be... No, let's see. 66 plus 16 is 72, 82. I need 6 more, like that. Okay. I might have done that wrong in my head. You can double check me. But basically, if we do that addition, then we get... 165 is the result there. Or is it? let's see, 165 minus 120. I don't want to think about it that hard. Let's see. Now, this thing, OneNote wants to keep doing this arithmetic for me, which is a lot of fun. Okay, so that should be 100 and... You know what? I feel like I did something wrong here. 128, 64. I think I just have that one bit out of place. Yeah. So there we get a 1. Now that's in what the sign bit would be for if we wanted this to be a negative number. So we have 1 there. It's going to be a 32. So 128 plus 32 is 160. Now I just need 5. See if that makes sense. I'm going to split these up a little bit just so they're easier to read. So yeah, that's 5. Yeah. All right. So that's what it is in binary. But that could also be, let's see, 37. So 128 minus 37. Negative 91, I think that makes sense. I might be off a little bit there. So if we're working with signed bytes, then this is going to wrap around to negative 99 or negative 91, or we want it to be 165. So it would be basically up to the software if the result is 165 or an overflow that wrapped around to a negative number. Because you probably don't ever want to actually add positive 77 to positive 88 and get negative 91. So your software is going to have to somehow keep track of that and pay attention. Now, in C programming, some of this is done for you, some of it is not. If you actually write just a plain C program and declare something as an int, and then you add 2 integers together that become larger than the maximum value in an integer, you'll get a negative result, or it'll wrap around. But it's not going to tell you that there's any problem. So I highly suggest doing that as an experiment, since all of you should know C programming. So So if you haven't done this before, do it. Go ahead and pause and just do it now. It'll take you 30 seconds to write a quick C program to add some numbers together. And you have the GCC compiler, so just write a C program that adds various numbers together and prints results. See what happens with different C integer types when you exceed the min or max values. Just take a look and see for yourself what happens. And again, you should Google find out those minimum and maximum values. All right, so that's enough for question and answer. That's the only one. I think there was another one that I sent an answer out in email to everybody. I don't think we need to talk about that here. So now, what are we going to do today? Well, basically, I need to drag this basic syntax page down here under week 4, and that's where we're picking up. We're talking about basic syntax in assembly language. And in particular, so we're basically talking about basic syntax in NASM. Oh, and by the way, before I get into that, let me just say one other thing. I've forgotten to give you official required reading, so I need you to start catching up in the textbook if you haven't been reading on your own. So read chapters 1 and 2 at least. For this week. All right, you've kind of gotten off the hook for reading for a while, so I need you to get caught up if you haven't already. So start reading those chapters, and then here in the videos, I'm kind of covering the same material, which is basically getting you introduced to NASM. So let me the net-wide assembler. This is just one assembler and particular assembly language syntax out of a few that are available. So there's not just one assembly language, but all of the assembly languages for, say, for example, 386 all operate off the same machine language. So it's just minor differences in syntax from one version to the other. The main syntax variations .386 assembly. The main syntax variations for 386 assembly are Intel, which is what we are using, and AT&T is the other one. Which we are not using, okay? Not in this class. There's not necessarily any particular reason to say one is better than the other. You just got to pick one and go with it. So we're going with Intel, and we're going with the NASM assembler. There are other assemblers that you can easily get access to, just as easily as we got NASM. So it's kind of up to you in the long run, if you ever do further work in assembly, what you prefer. You may just end up preferring the one you originally learned in, but it's very easy to go back and forth between them, so you'd end up picking up one or both of them anyway at some point. So at any rate, that is what we're dealing with, and so we're just going to look at basic syntax, and I think, did I actually talk about this? I think I talked about this somewhat, so I'm not going to go through this outline per se, at least not directly. What I want us to do is finally do some more hands-on work. You've had basically 2 weeks of just me talking to you in these videos without as much to actually do. So I want you to get to actually doing stuff again. So pull up your virtual machine or your preferred working environment, and we're going to actually install some new software here that I did not already have you install. So let's go ahead and do that. There's a couple things I want you to install, so we will have them to work with. One is KDBG, whoops, we need install there. Sudo apt-get install KDBG. This is the KDE desktop debugger. Let me go ahead and add that to the notes. Oops, Wrong one. There we go. So let me actually put this near the top. New packages to install in Linux. I thought I copied it, but I guess not. Let's get back over there and let's try that again. Copy. All right. There we go. And that's better. So we have sudo apt-get install kdbg, and we need to sudo apt-get install xterm. Those are the two things I want you to do. And I'm going to go with my style of, there. So you need to run these two commands. I've already done this here as I was experimenting, planning for this class. But so if I do it, the messages won't be quite the same as for you. As you can see, it's going to say, oops, might help if I actually type the right thing in. KDBG, that's what we want, and that's going to say it's already installed, already at the newest version. I suppose I could do a sudo apt-get remove KDBG, and then it's going to say, gonna uninstall all this stuff, and if I say yes, then all that stuff is gone, and then if I go up here and say install it, all that stuff will be back. So we want the KDBG, and the other thing you want is sudo, whoops, had a little background message there that it kicked in to me. This is not, I repeat, this is not a command you need to enter. For some reason, the install process pauses for a while, and when it's doing this setup, and then it kicks back this last message, and then it's done. That gets me every time. So at any rate, now we want to sudo apt-get install xterm. Fire that off. Now, again, mine's already installed, so I'd have to remove it if you wanted to see the messages, but I think you can handle that one. We want both of these, and then we are ready to be able to use the KDBG debugger. Whoops. That's another thing you might want to try install. It's a different editor called Kate, K-A-T-E. I kind of like it. I've been experimenting with some new things in Linux. That's actually where I found this KDBG tool. So let me throw a little bit in the notes as I talk about what that is. There we go. So let's see. Here I want to So we're getting the xterm package because it's something we need to make to get everything we want working in the KDBG product. But what is KDBG? First, I'll say, do you know what GDB is yet? If you don't, let me say what that is. GDB is the GNU debugger. All right, let's be more specific. Command line debugger for C, C++, assembly well, it's mostly, could be any language, but mostly those three on Linux. It's pretty much just your standard debugger for Linux. Now, some of you, maybe your only programming has been from 150 and 250, so you've basically just done a year of C programming, a little bit of C programming, not a lot. Your instructor may or may not have shown you a debugger, may or may not have shown you an IDE, so you may not have used GDB, you may have not used any debugger at all. We may take some time to look at GDB specifically, but just in a nutshell, what is a debugger? A debugger is something that lets you step through your program one instruction at a time and see what happens to the variables in your program. I mean, that's the essence of it. There's a lot of other stuff a debugger does, but that's the essence. Just think about, instead of having to add printfs into your programs, you just watch what happens to the variables one step at a time, as slowly as you need to make sure your program's working the way it should, or to figure out why it's not working the way you think it should be working. That's what a debugger is. So if in your experience so far you have not learned to use a debugger, start learning to use debuggers. Google about debuggers. Whatever programming language you work in, Google about debuggers and so forth. So, yeah, so, and also Google about IDEs, which include debuggers, for any language and operating system you work in. Okay, whether it's Windows, Linux, Mac OS, whether it's C or JavaScript or Java, whatever, start learning about debuggers and IDEs for whatever languages you work in. You're just crippling yourself if you don't do that, because you can write programs so much more easily, so much faster, if you work with debuggers and IDEs. So if you were not taught about any debuggers or IDEs in your first couple semesters of programming, now's the time to start teaching yourself. I'm going to show you a debugger that we're going to use for assembly language. I am not going to use GDB. We're going to be using KDBG. So what is KDBG? Mainly, it is a front end for GDB. Okay, it is a GUI front end, or a graphical front end. All right, so it basically is GDB under the hood, but it gives you a better visual presentation of what's going on. And I like that better for teaching purposes, and you will like it better for just actually getting work done purposes. And what I will say, it's a perfectly good debugger for C and C++, not just assembly. So, like I say, for your future programming needs, this is something that could be worthwhile. Now, some of you may already be familiar with other debuggers, other IDEs, but I want you to be sure you can do the same kinds of things that I show you here. So if you're using your own preferred tools and you cannot do what I'm showing you, you may need to just go ahead and get the Linux installed, the Linux Mint virtual machine, get it set up the same as what I have, just to make sure that you can install the same software and so forth. Now, if you are in a different version of Linux, you can probably find the equivalent packages and so forth. You may be able to do the sudo apt-get install KDBG in your own version of Linux, or the equivalent command. I think there's yum, and just depends on what flavor of Linux you're using. So in one way or another, you need to get this, or you need to get an equivalent. If you already know how to use GDB, you could do everything we're going to do in GDB on the command line, but why not get some get a feel for something that has a nice graphical interface on top of GDB, which makes it easier to use. So, okay, so that is what this tool is. It is a debugger. It gives us a nice visual interface onto the GNU debugger, and it's going to be a really excellent learning tool. So for our purposes, it's a good learning tool to understand what is going on in assembly language programs. And I'm introducing this now. Now, why did I just suddenly throw this in here? Because we're going to start learning the syntax. But really, all we're really learning is what the instructions do. The instructions themselves, the syntax is incredibly simple. But what is really important is you actually have to understand what those instructions do. What those instructions do is all about what we learned the other day in a previous video, this architecture, okay? Every instruction basically is just going to take data that's in registers or stored in memory somewhere. So you either have data over here in memory somewhere, or you have data in a register somewhere, or several registers. Each instruction is either going to do some calculation with data in memory or data in registers, or it's going to move data from memory to registers, from registers to memory, or it's going to do a little bit of both. It's going to move something from memory to the registers, do a calculation, put the result in another register, that sort of thing. Every instruction is going to be doing something along those lines, and so it's really critical that you understand what the instructions do. Once you understand what the instructions do, writing assembly language programs in some ways is the simplest form of programming. It's also the hardest form of programming. So it just kind of depends on how you look at it. Assembly language is very simple, but that makes programming kind of hard. So it's kind of a trade-off there. So, but you do have to understand physically what's going on, except it's not really physically, because as I mentioned, like even the memory we're looking at here in this diagram, this is virtual memory, not real memory. So it's not necessarily everything going on here has a physical process that's happening, but you might as well think of it that way. Okay, think of it. This is actually describing physically what happens to the computer, even if it's not really physical, it's virtual. All right, so with that in mind, let's dive into it. Let's start out with our first assembly language program that we already have, right? And I think I have it here. Now, one thing I did is I've renamed this first ASM stripped, where I've taken out all the extra lines of comments, okay? And let me put in a comment here to explain why I did that. Stripped because extra lines of comments and blank lines throw off the debugger. And I haven't figured out why this happens. So when we're using the debugger, and this happens to GDB, I found this happens with GDB, so it's not just a problem of KDGB, it's a problem with JDB. That if you have too many blank lines or extra comment lines and so forth in your assembly language program, it gets confused in terms of figuring out where you actually are, what instruction you actually are on in the program. And maybe I'll even pull up the other one when we get into this, just so you can see what I'm talking about. But for now, what I would say is take your first assembly language program that we created a few videos ago, open it up, do a say, keep that one with all those comments, because those comments make good notes and for the explanatory text there. But also delete any extra lines of comments. It's fine to have comments at the end of lines like this. These are no problem. But any extra blank lines and so forth, delete it down until you get to this. I do have a couple extra things here at the end. But for now, I don't want you to do those. I'll show you what those do later. So for now, you can type these in, or you can wait and type them in later. But for now, just take message and message len. These two are identical to what we had before. I've added some data down here, so we have a message to and a message to length here, and we'll mess with those later, maybe. But for now, just keep it to the original. So once you have that stripped down file, save it, and then we're ready to build it with the assembler and look at it in the debugger. All right, so to assemble it, the regular nasm command was nasm-f elf32, and then the name of the file. So here it is first assembly language stripped.asm, and that would be it. But we actually don't just want this. If all we wanted was to, whoops. What did I forget? Lowercase f. Yes. Okay. Message len undecided. Oh, I think it's a case sensitive thing. I had capital L here, lowercase l here. I think I'm just going to stick with all lowercase this time. So there we go. Fix that. Now, there we go. Not sure where -f, -m, and -F, different commands all use those for more or less the same purpose, and it's easy to forget which one's which. So yeah, we want the lowercase f here. So that's our regular nasm command, and then our ld command. ld dash. Why don't I just arrow up until I can find it? Yeah, it's -m. So -m, and then this is elf_i386, which means the same thing for the ld command as the elf32 does there. If I didn't explicitly explain it, this is simply saying we're doing the 32-bit 386 architecture, not the 64-bit architecture, and this is saying the same thing. 386 32-bit architecture, not 64-bit architecture. So then we want first assembly stripped.o, and then -o. There we go. So that gives us our program to work with, so we can just run it if we want, like so. But what we really want to do is run this into the debugger. But before we do that, we need to compile it with debugging symbols, or build it with debugging symbols. So here in our nasm, we want, let me make sure I do this right. There it is. There's the command we want. So I'm not typing it from memory. That's what arrowing up is good for, so you don't have to remember things. So you want this -g option and -f dwarf option. So -g means debugging symbols, and -f dwarf is the particular format of debugging information. So actually, I should probably bring these two commands over into the notes. So let me do that. So to run your program in the debugger, first build, that is assemble, with debugging info, and that is done with this command. Once you've done that, link normally, and this command. Like so. And I might as well, your program name here. Program name. All right. There we go. So that's the basic commands to build your program, your assembly language program. And once that's done, we're ready to run it in the debugger. To run it in the debugger, we can say kdbg and then your program name, the actual executable. Let me do a quick ls. Just say, okay, here is our executable file. So that's what we're running in the kdbg debugger. So, and going to put that in the background so that my terminal will still run. And this is the kdbg debugger. All right. If we hit run, it seems like, no, okay, it's there. It's not picking up the source, which, what did I do differently? Okay, I paused it there for a moment because I was trying to figure out what the heck I did. It looks like, as I go back through my old command, I didn't do the nasm command that has the debugging stuff, so that's what I skipped. Something you might do, so it's perfectly good that I did it. You get to see me make that mistake, so when you make that mistake, you're more likely to realize what you did. So we want to make sure that we have the -G and -F dwarf options in there. It looks like somehow... Oh, I know what I did. I arrowed up to them, but I didn't actually hit enter to actually rerun that command. So that makes sense. So the actual last time I assembled my program, I did not have the debugging information. So what's going on here, to make sure you understand the problem that I was seeing. So I'm running KDBG on my first ASM stripped executable, and so it pops up. What's missing here is this window right here that's empty. Should have the source code. So I should be seeing this file right here in that window, but I'm not, and that's because I did not build it with debugging information. So we need to do this. It's not the link that's the problem, it's that I didn't. Almost, there we are. So this is the version of the nasm command that we want to run. This will get us the debugging info. And so we build it with that. Now I still have to link it again, so let me arrow up to the link command. So here's the link command. Now it is built. With debugging info. Okay, got it? All right. Now I can run kdbg on first assembly stripped. Use the ampersand to detach it from the terminal and fire it up. Now here we go. Now we're talking. All right, so what do we have? We have the source code here, and I've worked with this before already, playing around with this before making this video, so it had that breakpoint in there. But what we can do here is we can set what are called breakpoints, and those are nice because we can run the program and then have it stop at a specific instruction in the program. for now, let's just put the breakpoint right at the beginning, okay? Right on start. That way when we run it, it won't actually have done any commands yet, all right? And we can see what happens one command at a time. So the simplest thing to do is just run, all right? So if you click run once, it runs up until the breakpoint. Now there's not actually an instruction on line 3, that's just the start label. The first actual instruction is right here, so that's where the green arrow is pointing, saying that this is the next instruction to run. And then you can step over. This is the one you most often want. We'll talk about step into and step out later on. When you start having function calls or subroutines, then step into and step out are things we want to mess with. Step into by instruction, step over by instruction, probably not things we need to worry about here. Mainly you want step over. Just think step over is your basic step, all right? So if I do step over, it does one instruction. Now right now, let's not worry about seeing what's happening. We're not seeing anything in output, locals, watches, anything. But, well, let's click registers down here because there's something going on there that we can actually see. We can see that it took the hex 18, that is the value of message length. Remember, that is the length of this string. What's down doc? Okay. 18 is 24. If we put that into hex, and if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Why does that seem wrong? I'm going to get 18 or 19. Oh, wait. That is an 18. It's a 1-2 hex. Haha. It's an 18 decimal. You got to remember what number system you're working with. So that is an 18. That's just a normal 18 there. It's a 1-2 hex, okay? And 1-2 hex is 18 decimal. So that makes sense. The text here, what's down doc, which we've partially coded in bytes, numeric bytes, and partly encoded as a string inside quotes, and then another numeric byte for the new line character. So that text is 18 bytes long. That's the value of this message len, and that's what we just copied into this EDX register, which is why you see an 18 there. And also notice that it's red, showing us that that register was updated by the last instruction. All right, and also notice that we have EIP here, showing us the address of the next instruction. So the address of this instruction right here is in hex 8048085. All right, which is similar. If you go back to the previous videos, that's exactly what I told you it was. So start would be 8048080, right? Or it's showing us in brackets another interpretation. That's start plus 5. Okay, so if we do another step, you can see it do another instruction. Now it moved the value of this into ECX. This is the address, is defined by this DB, data bytes keyword, defines this message symbol to be the address of the first byte of this data where it's stored in memory. So if we look at what we have there, in hex we have 80490A4. And so if you remember when we were looking in the bless editor, do I still have that? It's not there. Is that it? Yep, here it is. So remember when we were looking at this in the bless editor, we went first ASM program, the stripped program, and this should be, I think, just about identical. So, and we found the address of the .data section. So remember, each section of your program has a starting address. So we come back and look at your program. We have section text. The first actual byte in that text section is going to be this instruction. So that's the same as the address of start, labeling this instruction. The first thing in section data is this byte right here. which is also labeled by this address message. So the value of message is the address of the first byte of section data. And we figured out what that was by looking at the file in the text editor. We also could use the readelf command, if you remember. So if I do readelf first ASM stripped, and I want to use the -a option, just get all the information readelf's going to give me. Whoops. Script. There we go. And you see things like here, actually, that's the first address of the first byte of the data section, although it's not showing us that that's what that is there. Where is it showing us the actual sections? Yeah, .text, .data. Here it's showing us the address of the first byte of each of those. So we can see that that actually corresponds to what we, to what we are seeing in there we go. Got the window I want. All right, so that's what we're seeing here. And notice that the instruction register is now at start plus 10. So we're seeing the address of the next instruction. So we're seeing the address of this instruction. And you can step individually over instructions, or you can set breakpoints. And if you click run, it'll go through all the instructions until it hits the next. It'll just run normally until it hits the next breakpoint. So right now I don't have any other breakpoints, so if I want the program to finish without stepping through one at a time, I can just click run again, and the program just zip, it just finished. And you'll notice over here in this window over here, this is the output terminal for the debugged program, and it printed the message what's down doc, which is what this text right here is. And remember that these 5 commands basically set up a call to a thing called a syswrite. Might as well kind of change these comments. So, oh, I can't edit there. But if you remember from the discussion before, these 5 commands, the first 4 set up what's called a syswrite. And this one effectively calls that syswrite. And basically, by putting these 4 pieces of information in these 4 registers, we make the syswrite ready to go to do its thing, and it found this data here, and it printed that ASCII text to the terminal. Now, one thing you will see over here is this warning: GDB failed to set controlling terminal. This is a bug somewhere in KGDB or GDB, and the way it interacts with this terminal window. Free software, we just got to live with it. This does not affect anything you do. It's just going to be there. Just ignore it. Pretend it doesn't exist. So pretend that doesn't exist. This is the actual output of the program. The program finished. But you can put multiple breakpoints in. If we run again, again, it's going to stop right here on the first instruction. I can say get everything up to, so it's going to do these 5 instructions and then stop here because I put a second breakpoint. And all I'm doing to set these breakpoints is clicking over here on the side. So very easy to add a breakpoint or remove a breakpoint. And now if I click run again, it's going to do all of these instructions up to the next breakpoint. So there we go. And boom. And now all of these registers, see, we put the hex 12 or the 18. We put something into ECX. We put something into EDX and EBX. It feels like the wrong. Oh, and it did the syswrite. So the very last thing here actually changed that. Not the EDX register, the EAX register. So the EAX register had a 4 that we put in there, but it became the same as this. It's actually the number of bytes written, it looks like. So that kind of is a way that it indicates that it was successful by showing us a number of bytes written. But at any rate, that's details. The main thing is understand how breakpoints work, that you can click run to go up to the next breakpoint, or again, we can click step over to do one instruction at a time. and so on and so forth. And that just did the last instruction in the program. This is the last instruction, and the program's done again. And if we want to start it over again, we just click run again, and now we're at the next breakpoint. Or at the first breakpoint, I should say. So that's the basics of using a debugger. Now let's come down and look at this registers window. We have this decoded value and value. Value here is always displaying in hexadecimal, but it's not showing leading zeros. So like this 0, you should think of that as 0, 0, 0, 0, 0, 0, 0, 0. Right? Remember, each of these registers is 32 bits, which is 8 hexadecimal digits. So you should kind of think of it that way. But over here for the decoded value, we have a lot of options. For example, we can look at that as binary and just see it all as bits. Now here, only the selected one changed. If I select all of them and right click and say binary, now we see all of them as binary. There is one quirk that it leaves out a few leading zeros. Here it's leaving out 3 leading zeros on some of these. This one doesn't have leading zeros, so we're seeing the full 32 bits, but most of these are missing some leading zeros. It'll leave out 1, 2, or 3 leading zeros if it has that many. So there's some quirks with looking at this, but it's kind of nice to be able to see the actual binary values here that are stored in the registers. Maybe a little nicer to look at it as hexadecimal numbers. Here, I think it does not strip out any leading zeros, so we can set them all to hexadecimals. And now we're seeing all the registers. Now, you will see a lot of registers listed down here that we don't really care about. We're not going to necessarily look at many of these other registers other than E flags. That's one we're interested in. But other than that, we're mostly going to be working in this realm here. With these registers up to EIP. We might end up looking at these registers. These are for floating point numbers and floating point calculations, but I'm not sure we're going to get there in this class. So you have different ways of looking at it. I would think probably looking at these as decimal numbers, as, let me do them all at a time. So we could look at them all as decimal numbers, as hexadecimal numbers, or as binary numbers. Those would be your main choices for how you want to look at it. And notice that there is no signed or unsigned option here. That doesn't matter, okay? The CPU does not know whether the number integer is looking at is a signed or unsigned integer. As I mentioned earlier, that depends on the software to make that interpretation based on 2's complement. And is it going to look at it as a signed integer? Will it interpret something with a 1 bit in the highest bit as a negative number? So that's the basics of using KGDB to look at your running program. Now, now we can start getting into syntax and really using this to understand the syntax even more. So what I want to do here is click over here on another window, the memory window. All right, now what we're looking at here is the memory that starts at start. So notice that the address I have over here is 8048080. That's the value of start. And then we're seeing bytes of data. Right now we're seeing these as looks like we have them as decimal numbers and as octal numbers. And I really want to change that option. Let's make sure, let's look at bytes, individual bytes, but now let's look at them as hexadecimal bytes. And here we see we have BA 120000. Again, the 0x in front of each of these just tells us that it's a hexadecimal byte. So this should look familiar, for example, from our Bless hex editor view of this program. Remember when we found the first instruction, right there it is, okay, BA 12000000. Well, here's the same first instruction in the computer's memory at that address that we figured out that it was going to be at. And then the next instruction, I can't highlight here, but then the next instruction starts right here, B9 A4 90 0408. All right. Let's see. Now let's change the mode from bytes to words here. And let's see, I'm actually not sure it'll let me do this, but we can try. Yep, it let me put a start +1 in there. So I'm doing it at start +1 so we can actually see the operand and interpret it. So here's that first instruction, that first move instruction, which is move this value. Remember, that's a decimal 18 or a hexadecimal 12. All right, we're moving that into register EDX. So here we're seeing the number that we're going to move into that register. But again, remember, it's little endian, so the smallest byte, the last byte, is listed first here. And we see the same thing in the actual memory. If I go to bytes, we see the 12 is the first byte out of this sequence of 4 bytes right here. But if we go to words, 4-byte words, we see that it's interpreting that word as 00000012 because of little endian interpretation. So if we want this to be interpreted as a hexadecimal integer, then that first byte has to be the smallest byte. That has to be 1 times 16 plus 2 to get us 18 right there. That's the integer. And we can change this. Where's the option for decimal? Signed or unsigned decimal? Let's do unsigned decimal. There we go. Now we're seeing it as 18. And again, to get that interpreted, I had to go to words and I had to make start +1. If we go from start, then the words are not being broken up the way we want them. And we're mixing in the opcode of the instruction, this hex BA, that's the instruction itself, and we would be mixing that into the integer that forms this operand. And we don't want to do that. So that's why I put the +1 here, like so. Now there are other interesting things we can do here. You can choose instructions, and because this region of memory is storing the machine language instructions of our program, if I come over here and I say instructions, it reinterprets that machine language like this. Now, when you do this, incidentally, you are doing this, right? If not, pause, go back, do this yourself. Don't just watch, okay? Do it yourself, get screenshots, make sure that you're really understanding what's going on step by step, and you're able to do it. Now, if you're doing this, your instructions are not going to look this way. You're actually going to get what is called the Intel syntax. So remember, I mentioned the Intel syntax over here in the notes. Where is it? I mentioned that we are working with Intel syntax. I'm sorry, you're going to get the AT&T syntax. And we need to tell GDB and KGDB to use the AT&T syntax. So I'm going to show you how to change things so that you get that. So if you come over here to your terminal, and let's CD up into your home folder. So you want to be in your home folder, all right? And so you may have been down here in some classwork folder or something like that you created. You want to go to your home folder, CD tilde, like that, with a space. That'll take you up to your home folder. From here, we're going to find where is it? There it is. GDB init. You're going to find a hidden file, GDB init. You need this -A option on the ls command to see your hidden files. So ls space -A for all. You want to see all files, not just the normally visible ones. You'll see this file. Now, if we edit that file, You might need to create it. It might not exist yet. But if we bring that up in gedit, yeah, it probably won't exist. So what you're going to have to do, you want to create this file, .gdbinit. So run gedit or your favorite editor, create this file. It just needs one line. Set disassembly flavor Intel. Then you're going to exit and restart kgdb. All right. Actually, I'm going to take this out momentarily. Save and bring up my kgdb. I'm going to exit kgdb now. And come back to my terminal. I'm going to cd down into my documents folder and into my csc314 classwork folder. So here I am back. Now I changed my gdb init file so that I don't have that in there anymore, right? I've lost that. So now when I run kgdb on my first ASM script, and whoops. Oh, I misspelled it. KDBG. There we go. First assembly strip. Okay, that's what I want. All right, so we're running this now. Notice that it remembers the breakpoints that I had. That's kind of handy. So let me hit run, and now let's look at this memory listing, and I already have it in the instructions mode, but now we are seeing AT&T syntax, okay? So this is what AT&T syntax has, these extra dollar signs and percent symbols that has special meaning, and the Intel syntax just doesn't use that. And the other thing is, you'll notice like the EDX register, the destination comes as the second operand, and the source comes as the first operand. So it kind of reverses the order, reverses the order of operands. So it's actually pretty easy to translate from one to the other. So as soon as you know one, you start to learn the other pretty well. But we're just, to be consistent, we're going to work with the Intel flavor syntax for everything. So if you set disassembly flavor Intel in your gdb init file and save that, then come back over here. Let's exit again and come back in. So with that saved, I'm just going to do an ls-a on my home folder. So if you are not somebody who uses Linux a lot, then I always want to try and mention what's going on with these Linux commands. So this is the ls command to list the contents of a folder. The -a means show the hidden files. This says which folder to actually list. So normally you want the current folder, but if I want some other folder, I can just specify that. So here I'm specifying the home folder. And so this is showing me my home folder. There's my file that I just saved. That's the that basically is a file of things to initialize the GDB debugger with. I just want it permanently to use the Intel syntax flavor when it works with assembly language. And that way, whoops, I don't want that. That way, when I run kdbg and I come in here, now if we look at memory, if I hit run, then we look at the memory starting at start, and boom, move edx ox12. Looks much better. I think it looks much better that way. So, and here you can see the actual address of each of these instructions, which tells you how big they are. So like you can see this move edx12, that's going to take 5 bytes because the next instruction is, the address is 5 higher. So that's the next instruction, another 5 bytes, that's start plus 10, another 5 bytes to get to start plus 15, another 5 bytes, or it's start plus 20. But then this int ox80, that only takes 2 bytes because its instruction is right there at start plus 22. And you can also look at the hexadecimal addresses here and see that here it only went up from 9.4 to 9.6 in the last 2 digits. So it just went up by 2 there. Then this next one goes up to 27, so that's another 5 byte instruction. And then this is the last one, so we don't actually get to see. Well, okay, this is the last real instruction in the program, but there's garbage data or something out here, okay? Or maybe the assembler added this. I'm not sure if this is valid stuff or not. Probably not. I think not. But whatever data was out there can still be interpreted as instructions, and this just happens to be what instructions these would be. So these, everything from here to here, these are just garbage instructions. They're not part of the program. The last actual instruction in the program is right there. So let's see. So that's one way to look at data. Now you'll remember that message, that was that address 08, 04, etc. Now we might be able to get ampersand message here, but I'm not sure. Yeah, okay, it worked. All right, so it did know what message was. That's because it has the debugging info. So here we can actually see our data. Now here it's showing it to us. It defaulted to binary for us, but we can quickly go to bytes, or we can look at it as characters, as text. So here we see the W. See, it's giving us both a decimal version of the ASCII code, like 87 for capital W, 104 for lowercase h. But we're seeing the W, H, A, T, apostrophe, S, space, D, O, W, N. So it's what's down doc. So again, going back to our program, that's what we had. We had what's down doc here. Again, this is just an example that you can string together numeric values for bytes separated by commas, or you can put ASCII text characters inside single quotes. Either way works just fine. So coming back over here, we're actually seeing that data and where it shows up in memory by putting this in. We could also put in directly this address, like that, which is the same thing, right? So I can say ampersand message here. I could say OX08048080 because I know that's the first instruction in my program. That's the same as putting start. It does have a drop down where it remembers different addresses that you put in there, so I can always select one that I used previously. Now you'll notice here what you will notice here is that, again, we can interpret the bytes of memory any way we want. And it just depends on the program that you're running or what's going on, how they get interpreted. So it's because the CPU is going to look at this location of memory for an instruction, that is why those 5 bytes will be interpreted as an instruction and not as ASCII text or as a number or whatever. So I can look at these as individual byte numbers. I can look at them as groups of 4 bytes to form words, but that's really not the intention. But if I go up my address by 1 here, then this hexadecimal number 12, that is that number, okay? That is the number from the program. Where's my program? There it is. So again, message len, that is hexadecimal value of this number right here, defined here, is 12. It's 18 decimal 12 in hexadecimal. And that's what we're seeing there. Keep going to the wrong place. All right, so that's what we're seeing there, is the value of this right there. But now we're seeing it right there at byte position start plus 1. There's 4 bytes that represent that number. And again, if we look at them as individual bytes in sequence, we see that the 1, 2 byte comes first and then the other bytes later. So the smallest byte comes first, biggest byte comes last. But then when we interpret that, all 4 bytes together, interpreted as an integer, then, so I'm going to go words 4 bytes here. Then that set of 4 bytes gets interpreted this way. Or we can take those 4 bytes and we can look at them as a decimal number. And we see that it's an 18. Okay? And then this next word, well, that doesn't make any sense because right after that, that's right here, this is at start plus 5. So the first byte of this is the instruction. And then the next 4 bytes. So let's go back to 8, 0, like that. So starting there and go back to the bytes view here. So the BA here is that first instruction, then the 1, 2, 0, 0, 0, 0, 0. That's the number that we're going to store into register EDX. Then the next instruction, the instruction itself is B9, and then the number we're going to store is given by these 4 bytes after that. So that's starting at 7 start plus 6. So if I add 6 to this address, like that, now these first 4 bytes are the number that we're passing in there. So let's go back to words view. And there we go, 080490A4. That's that address. So message, remember, MSG is the address of this byte where it gets stored in the as the first byte of the .data section of memory. And that is this address right there. If I take that address, 90A4, 90A4, we already have in the list, we've already looked at it. So once again here, now we're seeing that data. Again, this is now broken up into words as hexadecimal numbers. Let's go to bytes. That's a little more sensible. And go to character, and then we see WHAT, the interpretation of these bytes starting at that memory location. So this command says move this address into this register. So we're storing the length of the text in one register, and then we're copying the actual address of the text to this register. Then we're going to put a 1 into this register and a 4 into this register. And you can really easily see that. If we go back to start, and here again we're looking at these as instructions, so we can see the move. This number is showing us the number in hexadecimal, which is just a 1, into EBX, and we're moving a 4 into EAX, and then we're doing the int operation here. Okay, so this tool is going to let us really see what each instruction actually does. So right now, and we kind of have already seen it, but just kind of review and to wrap up this video because it's already kind of long. Let's go ahead and again look at what happens here. So here we see what's in memory at this instruction. Move EDX012, or we can actually see it as bytes, hexadecimal bytes, like this. So we have the instruction BA, which basically moves the thing that comes right after this, the 4 bytes right after this, into register EDX. So we're going to take these 4 bytes here, the byte 12000000, we're going to copy those bytes into register EDX. So now let's go to the registers and see what happens when we do a step. So now we're ready to do this instruction. We do the step, and now we see in EDX we have that hex 1, 2. And if we come over here and we change the decoded value, oh, I want to change them all. To change all of the way all of the registers, the decoded value, if you want to change that, make sure you highlight this top thing here. Highlight that, right click, and then choose the decoding you want. So now that they're all hexadecimal, but we see that we just put the hexadecimal 1, 2 in there. Or if we want to see it as decimal again, we can do there, and we can see that we just put the number 18 into EDX. And that is exactly these 5 bytes right here. That is what that instruction does. It's the number 18. All right, from here to here, these 4 bytes, that's the number 18 as a 4-byte integer. And we're going to copy that number into register EDX. Now notice that in the registers, and I did mention this when I talked about little endianness before, in the registers there is no little endianness in the registers. The registers, the bytes are already in the order that makes sense. The highest order byte is the first byte, and the smallest order byte is the last byte. So endianness has to do with how you store the numbers in memory and how they get stored in data files. It does not, and so you actually, the hardware actually takes care of the reordering when that data gets copied to a register. So when you do something like a move command like this, it's going to take those 4 bytes and it's going to take care of the endianness so that the first byte goes to the last byte of the register, and the second byte goes to the second to last byte of the register, and so forth. So it takes care of the endianness for you when it moves the data from memory into registers and from registers back to memory. The endianness is handled for you. That byte ordering is handled for you. But I just wanted to kind of let you make sure that you see that step in action. I thought I would get further in this video, but there's just always more to explain than I realize, and I apologize to those if I'm explaining too much and going too slowly, but this has to be covered. I need to make sure everybody's up to speed on this. So, so what we have here is a way of looking directly at how each instruction affects registers and memory. So you can start reading about assembly instructions and then do experiments and then look at things in the debugger to make sure you really understand what's going on. I'm trying to say you don't need me. You don't actually need me to explain this stuff. You can start reading the textbook or Googling for other things that get example programs and so forth. So if you like learning on your own, I'm giving you the tools so that you can really do this and be able to do the experiment and make sure that you understand. Because if you follow what I've done here, you can just load any assembly language program into the debugger like this and go step by step and really make sure that you understand what did it do in memory, what did it do to the registers. Now there are more complicated things to understand about assembly language instructions, and that's what the next video we'll dive into a lot of examples of instructions and different ways that we can work with data, because there's basically 3 ways of working with things. One is we look at registers directly. Another is we have constants. So even though these are symbols, they're really just constant values that the assembler or the linker are going to calculate for us, or just actual constants. So there's registers, there's constants, and then there are addresses, or basically pointers. So from C, you would think of them as pointers. In assembly, we call them indirect. I have mentioned that in the notes, and this makes me think that I didn't go over this section of the notes yet about the operations. But yeah, when we start looking at the different kinds of operands, there's what we call immediate, register, and indirect. And the indirect are kind of like pointers in C. They're addresses of things, but you don't work with the address. You take the address and then you get whatever is in memory at that address, or you store things into memory at that address. So we're going to look at examples of all these things. And then there's also the question of the size, because although we normally would maybe work with 32-bit or 4-byte words, Sometimes we'll use instructions that just work on bytes. Maybe sometimes we'll use words, just 16 bits at a time. So we may end up using those. We have the extended, the EAX, EBX. Those registers are your 32-bit registers, but we will be looking at the 16-bit registers and the 8-bit portions of those. Remember when we looked at this diagram, and if we zoom in on the registers, remember you can work with the whole 32-bit register like EAX, or you can work with AX, which is half of that 32-bit register, or you can work with little 1-byte sections of that register. It just kind of depends on what you need to do. Because, the thing is with assembly language program, the registers are basically what your actual variables are to work with. So you've only got, let's see, basically 8 variables that you can play with here, 8 integers. That's not very many variables to do very much work with. So you're constantly, so you can't let these can never represent one specific thing. You can't just decide that EAX represents a certain thing in your program because you don't have enough registers to represent all the things you might want. For that reason, you're constantly, EAX, EBX, your registers are like temporary variables. And you're constantly swapping things in and out from memory, so you kind of have your permanent storage, or at least more permanent storage, out in main memory for your variables, and then you swap the variables into whatever register you need them in at a particular time when you need them. And the registers themselves work as temporary variables. So we're going to be looking in a lot more detail at a lot of different example instructions, and we're going to look at those in the debugger here so that we can actually see and clearly understand what is the relationship between memory, registers, and what any specific instruction does. So in our first simple program, very simple. It's copying some bytes directly from memory into some registers, boom, boom, boom. But we're going to look at more complicated variations on that theme, and we're going to look at add and subtract and jumps and so on and so forth. So that's what we're going to start digging into with the next video. This is video 1 for week 4. That'll be video 2 for week 4. Since this is already an hour and a half, I'm not sure how much more we'll do for this week. And I'll also be producing your homework assignment because I do need you to start actually writing programs on your own, assembly language programs, but we needed to kind of get this far before you would be really in a position to do that. So, and just again, as I said, though, I've given you the tools here that if you just want to start learning, looking up, following tutorials, reading the textbook, learning about assembly language, and then making sure you really understand what's going on, now you can use this debugger to actually just try out a command and then see what changes in memory, what changes in the registers, so that you actually know whether or not you really understand what these things are. Okay, so hopefully I've explained this pretty well. If you have questions, send them an email, and I'll try, and at the beginning of each video, I'll try and do a Q&A based on whatever questions have come in. There might be a few days between the time you ask the questions and when the video goes out with the answers. So just kind of depending, I may also send out answers in email or add answers to the notes, but do send questions. Anything you have doubts about that's not clear in one of these videos, you send me questions. Everybody in the class can probably benefit from those questions, so don't hesitate to send questions. All right, thank you. I think I'm going to end this because it's long enough, and I'll be picking up the next video soon.